Good afternoon. Let's review the area moment of inertia calculations for a basic rectangle. We'll then look at the area moment of inertia of an area underneath a function, and then we'll validate that calculation using CAD. So the area moment of inertia with respect to the centroidal axis, I probably should have a little sub x here in this definition. Area moment of inertia with respect to the centroidal axis of this rectangle is y squared dA. In other words, the distance squared to the centroid times the area. And of course, the area being in units squared and the distance squared would give us units to the fourth power. And in this case, if we wanted to determine what that equation is for a rectangle, simplified equation, we could use this differential element and integrate it from a minus h over 2 to a positive h over 2. So we have y squared. That element area would be b times dy. And so b is a constant. We'll move that outside the integral sign. Then integrate y squared becomes y cubed over 3 from a positive h over 2 to a minus h over 2. If you say inputting this value into the y cubed becomes h cubed over 8, and then a minus becomes a positive h cubed over 8, all over 3. Simplifying that becomes bh cubed over 12. And if we move that to the x-axis, assuming this is our x-axis down here, in other words, what's the value of area moment of inertia with respect to the x-axis, we can use the parallel axis theorem. So area moment of inertia with respect to the centroidal axis plus AD squared, this is the parallel axis theorem. Our area is base times the height. This is our area moment of inertia with respect to the centroidal axis, plus AD squared. Our area is base times height. The distance we're moving is 1/2 of h, and we square that. So simplifying this becomes 1/3 bh cubed. So the area moment of inertia of a rectangle with respect to the centroidal axis is bh cubed over 12. The area moment of inertia with respect to the x-axis, assuming this is the base along the x-axis, is 1/3 bh cubed. So why area moment of inertia? Why do we need to determine what the area moment of inertia is? And please don't confuse area moment of inertia with mass moment of inertia. A common equation where we use area moment of inertia is in the calculation of flexure stress or bending stress. We use sigma, same Greek letter that we use for normal stress, but in bending stress, it's mc over I. The magnitude of the moment times the distance from the centroidal axis over the area moment of inertia. So we can say that the maximum or average bending stress or flexure stress is directly proportional to the moment, the product of the moment and the distance from the neutral axis, and inversely proportional to the magnitude of our area moment of inertia. So in one sense, we can think of area moment of inertia as a resistance to flexure stress. When it's in units to the fourth, it becomes a very difficult number to get our minds around, abstract number. But if we look at it in terms of its use, we can think of area moment of inertia as a magnitude or a value of a cross-section of an area that will resist flexure stress or bending stress. Another common use that we'll use later on is in the calculation of critical buckling load. And this is for a pinned column. One end is pinned. You can calculate the critical buckling load with this equation. And notice that in this case, area moment of inertia is directly proportional to the magnitude of the critical buckling load. So the larger our area moment of inertia, just as in the larger of our modulus of elasticity, the stiffer the element and the larger the area moment of inertia, the larger critical buckling load we can have. We can carry a larger load before that column will buckle if we have a larger area moment of inertia. So let's now review a problem that will calculate the area moment of inertia of this area underneath this function. But let's first calculate its area, its centroid, x and y, and then we'll calculate the area moment of inertia about the x and the y axis. So the area underneath this function is just dA. And we'll use a vertical element. And so our width of the element is dx, and our height of the element is y. So y dx, as we integrate from 0 to 4, I probably should say y dx, but we convert y, change y in terms of x is 1/32 x cubed, so we can substitute that in here and integrate it from 0 to 4 becomes 2 inches. So that's the area underneath the function. Now the element, or the centroidal axis with respect to the x-axis, you use the equation x dA all over dA. And of course, we can use the 2 here as our area. And then x dA, we say x times dA, and dA again is 1/32 x cubed. That's y dx right there. So x times x cubed becomes x to the 4th. We can move 1/32 outside the integral sign, and integrating that becomes 3.2. Our y bar, now if we notice that the centroid of this element is 1/2 of y, right through the centroid here, it's 1/2 of the height of y. So in this case, we have to say 1/2 of y, because we're looking for the centroid of the shape. And of course, we need to integrate this using our y tilde, if you will. So we say 1/2 of y dA, move 1/2 out, and y is again 1/32 x cubed. And then dA again is y dx, and convert y in terms of x. So we have 32 times 32 times 2 becomes 1/2048. And x cubed times x cubed becomes x to the 6th all over 2. Integrating that becomes 0.571. So let's we'll validate these numbers also in our CAD system. Let's calculate the area moment of inertia with respect to the x-axis. Now, because all the x elements, the element inside this element change as we go from 0 to 4, we have to first calculate the moment of inertia with respect to the x-axis. So let's use the 1/3 bh cubed. If we used a horizontal element, we could just use the y squared dA, but because then all of the particles in that element have the same distance, the centroidal axis has the same distance to the x-axis, where here they change, and so we first have to calculate with respect to the x-axis. So 1/3 BH cubed converts that, or H cubed is our Y cubed, and our base is just dx of the element. And if we integrate that, 1/3 Y cubed becomes x cubed times x cubed times x cubed, that's x to the 9th. And 1/32 times 1/32 times 1/32, right? That becomes 32,768. And if we integrate that, the magnitude of our moment with respect to the x-axis is 1.0667. If we then move it to the centroidal axis, we just use the parallel axis theorem kind of in reverse, don't we? We'd say if we're moving it from here to the x-axis, we'd have to say this value plus that one. But since we're moving it from the x-axis to the centroid, we say our value of the moment of inertia with respect to the x-axis and move it to the centroid. So the 1.0667 minus the product of our area times the distance we're moving it. And we're moving at the y-bar, so that becomes 0.414. Now, with y, with a vertical element, we can just say all of these particles of the element have the same distance to y, and so we can just use x squared dA. Just as in here, if we had a horizontal element, we could use y squared dA in calculating the area moment of inertia with respect to the y-axis. We just use x squared dA, and then we'll move it to the centroid with, again, the parallel axis theorem. But again, we have x squared dA, x squared, and then dA is y dx, and y in terms of x is 1/32 x cubed dx. Combining those terms, we have 1/32 outside our integral sign. X squared times x cubed becomes x to the 5th. Integrating that becomes x to the 6th over 6. From 4 to 0 becomes 21 1/3. Moving that to the centroidal axis, we have 21 1/3 minus the product of our area times the distance we're moving. In this case, we are moving at the x value, aren't we? Moving at 3.2 right up here. That's the distance we're moving it from the y-axis to the centroid. And so that becomes 0.853. And then the magnitude of our area moment of inertia with respect to the pole, or the z-axis, is just our area moment of inertia with respect to the centroidal axis in x and y. Add those two together, and we then have the area moment of inertia with respect to the z-axis. Well, let's compare these values in our CAD system and see if we get the same values. I think I've already got this in here, and I'll show you how to create that if you have trouble creating the geometry. So I've already created this one ahead of time. So let's just use our section properties and look at these values here. We have the area we said was 2 inches, that's correct. Our centroid, with respect to the centroid, is 3.2. Let's just go back and validate that. That's 3.2. Yes, that's what we got there. And y is 0.571. That's what we got manually. So there's our centroid, 2D. Now, this moment of inertia with respect to the x-axis, this is at the centroid, isn't it? See, that's at the centroid. So if we check our values there, we got 0.414. And again, we have to move it from the x-axis to the centroid to get the same values that we get here in the CAD system. So we got 0.414. And the y, we get 0.853. Manually, we got 0.853. And then about the z-axis, we get an addition of those 1.267, and that's what we got here, 1.267. So we want to be able to validate these numbers manually. In fact, this is a good practice for all of our calculations and analysis, is to have a system where we can do a check. If we do it manually, have a CAD system or an automated system where we can check our values, and vice versa. If we're using CAD, it's always good to do a reality check, because if our inputs are incorrect, the automated system, the CAD systems and so on, will just give us totally erroneous numbers. And it's good to have a feel for what these should be, because when you're going to be using these values in our calculations later on for both stress and critical buckling load. So we want to be comfortable in calculating these values. Well, I told you that I would demonstrate how to create these functions. This is from Hibbeler's Statics and Mechanics of Materials textbook, 5th edition. And I've already created this one here before that we used in our little tutorial. So let's just recreate that. If in the front view, this is in SolidWorks, I sketch and come up to spline, equation-driven spline, and the function on this was y is equal to, and I'll put in parentheses, 1 divided by 32 times, I use the shift 8, times x caret 3, or up 3, as I go from 0 to 4. And it creates that curve or spline that I can then close off with a vertical line and a horizontal line. And of course that gives me then the area that I need to use in this problem, chapter 6, review problem 6-5. And again, if we do the evaluate section properties here on that, we can see that these values, it gives me the area of the underneath the curve, it gives me the x bar, the distance from my origin out here to my centroid, and the y bar, of course, is from the x-axis up to centroid, this distance here. So there's my centroids, centroid about the x and the y. And then the area moment of inertia with respect to the centroidal axis, 0.414 inches to the fourth. With respect to the y centroidal axis, in other words, this vertical axis passing right through the centroid, that's the area moment of inertia about that centroidal axis. And there's the moment of inertia about the z, is the axis coming straight out at us from that point right there. If